data-driven maintenance. This event is brought to you in partnership with Network Rail and Ukraine, and as with all of the Unlocking Innovation events, it is open to everyone to attend and it is free on the door. As part of this event, we are collecting information to feed into the RTS, the Railway Technical Strategy, and we're after the contact details of any organisations who have technologies or capabilities around data-driven maintenance to feed into a big master log sheet of all organisations working in this space. My colleague Carl will place this link in the chat shortly. So if you are an organisation working in this space and you'd like your details logged on that sheet for possible future projects and business opportunities with clients' organisations, then please do pop over there. The form will only take you 2 minutes. It's just contact details and a description of the sort of things you're working on. Dead simple. Yesterday, we had 2 sessions. We're trying to frame the whole process of data-driven maintenance throughout the 4 sessions. So we started off with knowing your asset, which was all about the underlying asset knowledge you need before you even start taking measurements. And then in the afternoon, we had a session on collecting your data. So how do we get the data back from those assets? Those sessions were recorded and will be available online very shortly, probably by this evening. So if you weren't in those sessions, you can go along there and play those back. And all of the slides from the presentations will also be shared with those. Similarly, this session will be recorded and it will be available on our website afterwards. This is interpreting your data. And then this afternoon at 3 o'clock, you can join the 3 o'clock session on the same link as this session. And we're going to be talking about changing our business. What do we do after we've interpreted the data? How do we change the business to enable true reliability-centered maintenance? Got a packed agenda for you this afternoon and some great speakers. I've popped this slide up, but I don't intend to leave it on too long. I'd rather just get straight on and introduce our first speaker, Martin Mason, Programme Manager, Development and R&D on Intelligent Infrastructure at Network Rail. Martin's railway industry experience spans 2 decades, from frontline engineering roles to leading Network Rail's advanced R&D analytics team. Martin is currently leading a transformation towards predict and prevent railway maintenance through the development of track and signalling decision support tool capability, allowing teams to fix faults before they occur. So, Martin, would you like to switch your camera and microphone on?
Thank you, Sam. Hoping you can hear me and see me.
I can hear you. I will stop sharing my screen.
Thank you very much.
Hopefully that's stopped and it's all over to you.
I've brought with me today Stephen Carpenter as well, who's my senior systems modelling engineer. He's going to talk about the signalling offerings we have within our Insight product. So without further ado, I shall attempt to share the presentation. Can you see that? We
can see your PowerPoint. There we go. Perfect.
Fantastic. So we're here today. Thank you for inviting us to introduce you to our Insight product that we're building in the Intelligent Infrastructure Programme at Network Rail. And essentially, at a high level, Insight is a web-based product that we're going to deploy to multiple discipline engineers across Network Rail. And the idea behind it is that we leverage intelligence we already have from measurement trains and RCM fitted systems. We apply advanced analytics and machine learning models to those. And then the whole concept is that we want to be able to predict or understand asset condition as it is, and then when that condition will lead to a failure and potentially impact service to our customers. So the idea is it's a decision support tool. It's not a make a decision for you tool. So it's a way of presenting intelligence to engineers that leverages those advanced analytics techniques and gives them visualizations they can then use to confirm the analytic outputs that they're being presented to help inform their decisions around maintenance, capital works, and then leveraging efficiencies around working across a system, railway system, rather than disparate discipline working. And the goal is to obviously move maintenance from a reactive world where, as an example, a RCM bit of kit or a measurement train will tell you you're at a particular failure level, and give them enough time to move to be a reactive organisation, and that is be able to plan works or condition assessments in time before assets fail or reach a particular safety threshold. So I kind of touched on it before, but the key objective is to move maintenance up this P2F curve, which is a condition-based curve that measures how long it will take an asset potentially to move from a potential failure point where we initially pick up a reading to functional failure, where it will impact safety or the running of the railway. So the idea is that the algorithms we develop and the machine learning models are to understand these curves for different types of assets and to give operatives enough time to then plan maintenance. So that may be in the example of track, we give them 90 days to be able to effectively plan a possession. With things like track circuits and signalling assets like POE, we're looking at giving a 7-day, which should give enough time to then action a visit to the asset and potentially understand the failure. As well as on top of this, what we're trying to do is leverage all the other intelligence we have cross-discipline through our failure mode analysis to be able to support root cause, to be able to provide intelligence around not only when the asset's going to fail, but potentially what you're expected to find when you go to assess the asset and its condition. So the product itself is built around core functionality, UI and user experience. It's a role-based product. So as an example, the user would enter as a track section manager, which you can see here, and instantly the product directs you to areas of concern that you need to very quickly deal with. And the idea is that the user journey or user experience is designed in such a way that you get efficiency from the product. And as an example, you should be able to drill into where your headaches are, and the visualizations of the outputs of the analytics should allow you to very quickly make a decision on whether you want to react to it or whether you want to just sit and watch it, or whether in fact you want to close it if it is indeed a false positive. So the first release we've gone through is for track, and this is about leveraging the intelligence we get from our measurement trains to collect geometry, images around pattern recognition, ground penetrating radar, and it's around giving users extra intelligence on what they get in their reactive or paper-based world, to allow them to then not only move up the P2F curve, but to give them the visualizations they need to be able to support the intelligence you're giving them and then react in the right way to that intelligence. So you can see a couple of views here. One's around a run-on-run trace capability. So in the track world, operatives get a trace per run, and then they measure across that to understand where their problems are. The algorithms we've developed allow us to align those through space and time, which has always been a challenge. And from that, we can then create regression models, understand the P2F, and then we design the product with the user as the key inputter to the requirements about how do you want to interact with this intelligence, what are the visuals you need to be able to support making a decision, and then what are the kind of functionality that you need within it to be able to then understand root cause and then book the most effective and efficient maintenance to deal with not only that problem, but obviously giving you enough time to understand when things are going to occur means you can actually look at the problems in that area holistically. As an example, you might be driven in the product to look for a twist fault, but at the same time having that extra time allows you to say, I've got missing clips, a wet bed, and you can build an optimum intervention around the site. And alongside that, we get an inbox that users can use. So it's not an inbox in the sense of an email, but it holds actions that the users are required to take, and it will group these types of defects for them in a way that they can then manage them holistically rather than individually. So it's a agile development, what we're doing with this product. So we do a release and then customers feedback improvements, which we'll implement quickly. And then we move on to other releases around rail management, etc. So what does it give users today? Well, it gives them automatically aligned traces with P2F curves that produces alerts for them every time the train runs. It gives them these unique visuals that allows them to turn on and off traces, step forward and step back, and look at different parameters of geometry to look for trigger points or root causes. It gives them the ability to predict threshold exceedances in the future, and then be able to prioritize around what they have to fix today, as well as what in that location will they have to fix in the future. A unique view around cyclic top, which is a fault type that causes a lot of speed restrictions around the network. And it's a unique view we've developed with the customers to allow them to enable that effective understanding of trigger points and where in the railway you need to intervene to stop repeat issues occurring, as well as a hopefully if I get this out of the way you can see the bottom of it, as well as predicting cyclic top threshold exceedances, which is an accumulation model that we've not had before, and the customers are using now in anger, and obviously the whole point of Agile is they feedback improvements or potential issues that we can then work on and roll out improvements around the product. And I'm going to hand over now to Steve. So Steve's going to talk you through what we do with our signaling RCM data that comes off of our loggers, and how we're using that going forward to then use the common user journey through insight action pages to then allow users to predict issues with the signaling assets. So over to you, Steve. When you need me to move on, just say next.
Okie dokie. Thank you. Good morning. So we've been looking at point operating equipment and track circuits, and we're getting the trace data from Wonderware. We've got 3 years worth of data. We're now looking at how we analyze those traces. So we're trying to understand what does a good trace look like, and then what does an anomalous trace look like. So we worked with key business users to understand all of the influences that can be had on a PoE trace. So if the switch size can affect it, whether there's a back drive installed, whether there's switch rollers installed, a number of key factors, and taking all that into account, we then trained a machine learning model over what was good. And then what we've then been able to do is, with another year's worth of data, we've been able to test that and then check that against our failures that we've had, so that we can then start to understand, is the model achieving what we need it to achieve? So we're able to then take that to the next level, where we're then looking at 3 days prior to a failure and saying, are we seeing lots of anomalous traces in those previous days, which allow us to then make a prediction that something is starting to trend off with regards to that PoE or track circuit. So we'll go on to the next slide. So as I'm not sure if all of you are aware, this is a layout of the S&C. As you can see in here, we've got the point machine on the right hand side, and the Wonderware traces are from the current of driving the point machine. Now, there are different types of point machine out there. There's clamp locks and HWs and all sorts of different types. They all come with different trace patterns. And we've also got back drives on here, and I can't see them, but they may have switch rollers on there. They all have given us different patterns. If we go to the next one, so this is just a typical layout of a track circuit. It's very difficult to actually get a photo of a track circuit because of what it is. So the principle is here, where a train not on it, you've got an energized relay. And then when a train is on it, you've got a de-energized relay, and the Wonderware traces are looking for that, telling us how long it's down for, how did it transition from unoccupied state to an occupied state, and we're looking for differences in all of that information. So if we move on to the next slide. So what are we doing within the Insight tool? So we're currently going through the phase of working with all of our key business users on working out what information they need to see when making a decision about whether a trace is anomalous or not, because it's not only the trace, they need to understand key information around the asset, like I've mentioned, but they also want to know, when did it last cause a prediction? when did how is that asset trending? How many times does that set of points get swung in a week or in a day? And when it was swinging, what was its average current? What was its time that it took to swing those sets of points? So what we've got here is we're now showing the users, we've similar to what Martin had, we had an inbox that drives you to a prediction screen. Within that prediction screen, we then show them a list of the different predictions, but they click on one. You then get to see all of your previous predictions that have happened. They're all got a priority on them that will be looking at the FOAS, the risk scores, the impact scores that will be driving where these need to sit. They've also got a screen not shown here which tells them all about the information. Is there a point heater, the type, etc., etc. So this gives them a good steer of what was there. We've then got all of the traces. Now at the moment we're only showing so many. The plan is to give them, they wanted to see 12, and you would be able to switch these on and off and add more. You can see here as an example that you can see just that one trace is fairly quick, the others are starting to extend out. So they would want to be looking at, hang on, what's happened between there and between those swings to start to understand that. That's where you then lead into the 28-day trending. So you can then start to look at that and say, has that been happening over a long period of time? Is it starting to, when did it start to trend off? And then they'll be able to start to look in, we haven't got the screen here, but we've got a workbank summary where they can then go and look and say on, you know, the 1st of July, what was happening with my asset? There was some maintenance from track team or the signaling team. They would then see that trending off. Now, as something that they've done caused that, and we need to go out and correct that with the right intervention type. So then we've also then got an efficiency radar. So this is now looking at all of the other types of points in the same category as the one that you selected, and it's looking to see how long it's the difference between the normal and the reverse for all of those points. So you can then start to look and say, well, yes, it's trending off, but all of the other points did the same thing on that day. Now that may be due to rain, it may be due to the sun or the heat or another factor that we're still looking into. So we're bringing those in from the FOAS work, and we can then start to go, oh yeah, I've got that one, but hang on, I've got another one that's trending off. I might want to go and look at that. So we're able to then drive different thinking behind seeing all of this data, because at the moment they have to go to multiple systems to see it. So we're trying to bring it together all in one place so that they can make their decisions as effectively and as timely as possible. And that's, I think, is there one more slide? I think that's it for me.
Thank you, Steve. So hopefully that's giving you a flavour of where we're going and what we're trying to do. Obviously, we've picked critical asset types around safety and impact customers first, but the concept is that any RCM fitted kit or any data that we can collect off the railway can then be incorporated into our models and then add extra features in. And the key take is it's a decision support tool. Hopefully you've got a flavour for the fact that everything that we do within this space is driven from our frontline staff. So it's about presenting the intelligence in a way that each of them requires it in order to get the most efficient journey through and optimise their working days, so they're not spending hours and hours looking at different systems, as Steve mentioned, but they're out doing what they should be doing, which is maintaining the railway. So hopefully it's giving you a flavour. We'll send the slide deck out, and hopefully we've left some time, Sam, for some questions.
Thank you very much. That was real good stuff. You have indeed left some time for questions. Perfect timing, some might say. We've got some questions popping up in the chat, and then I've got a whole sheet full of questions that I've created while you were presenting. I used to work in this field, so it's all of great interest to me. First of all, from Ant Monaghan, Regarding the prediction of failure, how do you use the curve? I assume he's referring to the PF curve. How do you use this curve for electronic components which have a very short degradation from initial failure indicator to failure?
So I think what we've got to do is it's about focusing on the things that you can use the intelligence on, where you've got enough of a lag across the P to F curve to give an operative time to respond to it in the right way. There's always going to be kit out there that we would just expect an alert or an alarm, and then we go and essentially the action is replace me. Where we've got assets where you've got kind of got a longer lead time, and we can get a longer P2F, or at least enough time to be able to go and react or do a condition assessment, that's where we initially focus our time. And then as we get more intelligent around linking P2Fs together across different disciplines, we may be able to find intelligence in other bits of kit that's connected to, that then can give you that key indicator with enough time, and then we bring all that together. So hopefully that's answered the question, but it's about focusing initially on the analytics to prove that you can give someone enough time to respond, with enough leeway to be able to get the resources, plan the possession, and then potentially come back again with signalling assets. You might have to go and then do your initial assessment and then plan what you're going to do after that. So hopefully that's answered your question.
Okay. Matt Bruff has said, Insight looks like a great tool, and I agree. Does it give any view on root cause of groups of issues at a location?
Yeah, so the concept is, obviously we initially focus on things that are coming off the train at the moment, and we have a process around. As we build that, and the track example is a really good example, we're starting to bring in other intelligence like earthwork condition, track components, wet beds, drainage condition. So it's about saying, in that location, as an example, this twist fault's going off quicker than it should do, or what we perceived it would do, and then giving the intelligence to say, it's on an embankment, the weather's been rainy, there's a wet bed, the drainage is in poor condition, as an example. And then it's about building that cross-discipline intervention workbank that says, I might be able to go and straighten the track up, but if I don't fix all the other issues at the same time, then it's just going to keep happening and cause repeats. And then that's when you start passing delays on to customers, as an example.
Okay, so just to echo that, Matt says, Insight looks like a great tool, and I agree. Just looking overseas, has any other infrastructure owner got any tool like this? Are we world leading? Is there an export opportunity?
I would like to think we are, especially around the cyclic top and geometry predictions. I think the concept of the product works for multiple industries, as an example, if you use role-based or discipline-based team structure. So yeah, I would say a lot of the experience I've had over the last 15 years, we've kind of been looking for this intelligence or the ability to do this. So I would say from a network rail perspective, I would definitely see it as kind of world leading.
World leading, excellent, great to hear. So your presentation focused on identifying faults before they transition to failures, but is there also, with this knowledge, the opportunity to relax your periodic inspections? Because I assume that you're still performing, with points as an example, you're still performing your checks, so you're just trying to spot the failures before they occur. But if you have the knowledge of the asset condition, have you looked into relaxing those intervals perhaps? So
a lot of it is the outputs of analytics, right? So we have concepts that we're working on now for our risk-based maintenance for track.
Yeah.
So as an example, you can use that intelligence to set local thresholds. And obviously, as time goes on and you get confidence from the intelligence, and you can back that up with analytics that says, we're 70% true positive, blah, 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 you can then start to look at enhancing or using that analytics to then look at the standards and potential relaxing, but it's more about the RBM and using the intelligence to then be able to drive those regimes, like you mentioned, the cyclic maintenance. It's about saying, for a particular asset, does the intelligence give me the confidence to be able to then be more flexible with my inspections? But they're all safety critical assets.
Yes.
So obviously the analytics is key to being able to drive those conversations.
And I guess proving that case that your knowledge and analytics is sound is what will enable the another level of savings to come from relaxing those periods, or?
Correct.
Yeah. Just got a couple minutes left. I've got a couple of questions for Stephen, if I may. So I'm interested in your AI that you've trained for your points operating equipment, and what level you trained that AI at. So did you give it the entire data set of all the points on the network and had it classify whether it was a clamp lock or a HW, or did you give it individual point machines and it had to count the rollers, for example?
So initially what we did was we've bucketed each of those different types first. So we took the data that we have in our master asset system, we took the key attributes off of that, plugged that in. We knew, you know, we had C switches and we knew they had switch rollers on, and then we started to look at training the model over that specific set. So we've not taken the whole country, we took a specific area to start with. We're building on that now. I think we had about 800 ends that we put through that we were getting the results back on. So that's what we're looking at. So when we get the traces in, we're looking at what asset they belong to, and then we're able to assess what model they will run over as we train it. So
there's a level of human intervention at the moment before the data gets handed to the AI.
Well,
for the bucketing.
Look, for us, yes.
Yeah.
When we were starting out, we were doing it manually. The plan is to automate all of that in the solution that we've finally come up with. So it will be taking what we have in our master system, looking at those and going, it's in that bucket you need to put it.
And have you developed this internally, or is it in with supply chain? Have you done it in partnership with supply chain?
Yes, so we've been working. So it's in partnership with our delivery partners. We've got a Cognizant. We've got a data science team there. We've got our SMEs that sit, me and Andy and Paul, that sit with us, and we're looking at all of that, and we're helping them to bring that together. And then we go to the business and get their key inputs, and they're saying bucket this way or do it this way, try this. And then we've done all of that, and then we've come up with the model.
What's interesting is it's quite generic. So what we thought was, Sam, that you would have to have really low level attribute data against each set of points. What we found was, once we started modeling them, data quality plays a factor. So some points are categorized incorrectly in the system, and you would put them in a bucket that you found out they're in the wrong bucket, but actually the model still is working at the level of success against that. That means it's still viable. So as we get data quality improvement, we would expect to see a massive improvement in that model. So I would say it's quite generic because of issues we found with data quality. But in terms of the different types and the outputs, we haven't seen a degradation in in true positives or an increase in false positives, which has given us a lot of confidence, obviously. Yeah,
I believe so. Excellent. Great. So 10:30. Thank you very much, Martin.
Pleasure.
Thank you very much, Stephen. Really interesting stuff. Please do stick around to the end to the informal networking and hear the rest of our presentations this afternoon, if you are able. And for the audience, if you have any further questions for either Martin or Stephen, please do pop them in the chat, and they'll be able to answer them directly there. But without further ado, I'd like to introduce our next presenter, Christoph Schuessler. So Christoph, if you could pop your camera and microphone on for us, please. Christoph is a data scientist at Siemens Mobility. He's been in the railway industry for 7 years in the signalling and rolling stock field, and his current specialisation is rolling stock diagnostics, remote condition monitoring. He's also a part-time railway systems engineering and integration student at the University of Birmingham. Hello, Christoph.
Hi, thank you very much for the introduction.
Over to you.
Thank you very much. I'm going to share the screen, one moment. I'm going to share the slides.
I can confirm we'll see those. We can see those.
Perfect. Perfect. Thank you for the feedback. Well, thanks again for giving me the chance for this presentation today. The content today for this presentation is a quick summary of myself, digital service, so my department, Radiant, if you maybe already heard from our ecosystem. The second part of the presentation will cover the development of the RCM, and last but not least, a little outlook and challenges along this development. Yeah, I might skip this one here since Sam already covered more or less everything. So I go on directly to digital services as a department. So what are we doing in our department? You can see those pyramid on the right hand side, which provides a symbolic pillar on the bottom, which are the enablers. And what we're doing is a part of this is providing support in retrofitting state-of-the-art sensors to legacy fleets, so that we make help to get the connectivity between the train and the land side, to even be able to get the remote access to send data and to provide this for analytical purposes. The second step or the second pillar is standard reporting, such as fleet monitoring or train state live. These are tools, for example, fleet monitoring to monitor your whole fleet in service, and the positioning. Train state live gives live feedback from the current state of the train. And bespoke system diagnostics are therefore could be similar to those standard reporting, but with a customizable part of it. So if a customer wishes to see even more than the standard application has embedded, then we can also increase this kind of application with a customizable part. Also more diagnostic focused solutions, and the highest part of the pyramid will cover the custom advanced analytics, which probably the current presentation would fall in terms of remote condition monitoring. Some of you may heard already of Religent. Religent is our open ecosystem and our central point for rail applications. So every application developer in Siemens is part of Religent. And we can also provide access and services for third-party companies in there. So if a company wishes to make use of the data within our Religent ecosystem, then this is also possible. Well, coming to the main part of this presentation, this is kind of a high-level summary of our first approach we made for remote condition monitoring for the doors. The initial situation was actually that we knew that there is a certain issue on the doors, which we wanted to make sure that we can proactively see those abnormalities before a failure happens. So this was a really interesting task for me as a data scientist, because I could leave my laptop, my desk behind, and could attend on the train, and did some testing with technicians, with experts, and we tried to create some sample data. So this was a really manually task to really get a data set together, which could indicate limits of where the data can go, and where the traces which we then later on acquire from those doors, where do we put the limits on? And this was a really interesting task, but at the same time this needed to be quite a quick turnaround, because we needed this solution quite early in place. So what we did, we developed different threshold levels of abnormalities in the data, and this helped us to define an indication, a condition indication for each door. At the same time, we developed also a dashboard for this, so that everybody within the company or technicians, they were able to get the results of this algorithm by themselves by looking into the dashboard. But to make a proper use of this algorithm, we implemented a monitoring and maintenance process for this. So this was a 24/7 application, which was scanning and monitoring all doors of this specific fleet in service all the time. And whenever a certain threshold was extended or was hit by this condition indicator, we created digital work orders based on this, and those work orders were then directly feed to the depots with different priorities as well, because those condition indicator could be if you talk in rec status, this is either green, for example, yellow or red, and depending on this, we can set different priorities that either the maintenance needs to be carried out directly, or it's more like an alert, and we know we can wait a bit. But this was more conservative to just make sure that we see any trend before the failure actually happened, to be really able to proactive detect this. And this was also one of the improvements and kind of evaluation we did on this we were able to identify those issues in a really early stage. The true positive rate was about 85%, but I maybe can say more about this at the end. It looks already quite good, but there's still like potential to increase this to, to 100% if you got a really proper system in place. But the whole process helped us to optimize the maintenance. We were able to allocate the problem more direct because the data was telling us where the problem occurred on the door, and therefore we could reduce downtime and increase the reliability. So this is kind of the first use case we had in place. But as I said at the beginning, this was developed on a specific issue we had and not set up in a way that we could, for example, get also a true positive rate out of it. So the next step we did was to, based on the experience we made with this first model, to implement a more precise and more detailed model for analyzing the door's condition. And for this, we made use, as I said, of the experience of the previous model. And one major step we did was to eliminate or to pre-classify the data that we can already know. We have to know what represents a good door and a good door movement, for example, compared to a bad door. And in this case, if you can see the visualization, this is a regression line from a regression model we use to identify those outliers or those residuals. And you can see the position of the door in millimeters on the x-axis and the residuals on the y-axis. And even though the data, the traces we get from the train, there are only 15 data points over the whole movement of the door. But since those movements are always shifting with every activity of the door, we get a really dense data set for literally every millimeter of the door positioning, depending how much data we take into account. And this here is just a data set of a couple of door movements, just for one door and for one type of movement. So this is just for the opening movement of a door. And you can clearly see that we have for every millimeter a data set, a data point, and the regression line indicates this big outlier here, which can be seen in the R squared value, which we use in the first stage as a condition indicator for this model. How we can make use of this data for maintenance purpose. So, as I said before, we could see differences in door closing and door opening. And this was really interesting to find out those patterns, that they differ so extremely that, for example, in this case, you can see that the door closing was constantly in an ideal state. So this was always close to 100%. But at the same time, we could see that the trend of the door opening is dropping. So the condition of the opening door was dropping. And usually we would assume, if we take all data into account for one door, we would take maybe an average of this, and then we would think, okay, maybe it's not that bad because we have like more than half of the data looks perfect, but only another part of it looks not as good. So it was really important to distinguish between those two movements to be able to detect even preciser issues. And coming, the next slide will show the maintenance effectiveness of this door movement for the opening phase, whereas we can identify and quantify a maintenance task if they have been carried out and if they have been successfully carried out. So this is kind of a feedback we can receive. Someone is whistling in the background.
Anybody who's got your mic turned on and is whistling, please just switch that off. Thank you.
I hope it's not too boring what I'm presenting, but where did I stop? So the maintenance effectiveness is something we can quantify with this algorithm. So we can clearly see whenever a maintenance was carried out, if this was successful. So in this case, we know that there was a exam carried out on the 2nd of June, and the value has been going back, the condition back to 100%. So this is a really good feedback we can provide for the operators or the maintenance operator to know if they have done their job good and if they're like confident bringing the train back into service. But this kind of data, we can also make use of it directly, because when is the biggest value of the data is when we make use of it directly. So the newer the data, the higher the value. And with the help, for example, of Redigent, we are able to provide this feedback in less than 3-4 minutes. In the worst case, maybe 5 minutes. So ideal would be that this feedback goes back to the maintenance supervisor or directly to the operator to give them the feedback immediately when they're doing this maintenance task. For example, they can finish, they adjust the door, they do the calibration, the creasing and everything, and then they run the door, they open and close it 3-4 times, takes a couple of seconds, and then 2 minutes later they can get back the feedback from the data saying them, yes, the door looks fine, no worries that you have to readjust something. So this is something additionally where we can make use of this data and this kind of algorithm. And of course, prediction is always one of the biggest topics. And as also here, we can make use of a prediction model to analyze this data and to analyze the trend. Clearly to see on the top with the closing phase of the door, where the prediction will be static on 100%, but the trend looks different on the opening phase of the door. And the really crucial part, and this probably fits quite nicely to the previous presentation, is to analyze this PF interval. Where do we know where's the P and where's the F? So this is something I realized by using the data. It differs from door to door. And the reason why it differs is at the end, because we have different type of failures. And that's why we thought, okay, let's make sure that we know what type of failure might be on this door when we analyze this condition, because then we can set different thresholds, different P and different F levels and limits for the specific issue for the specific door. And to analyze this, we used a statistical function, a Gaussian distribution, to determine essential attributes, which can give us an indication of the type of failure we have. And those 3 attributes are, for example, the central position, which is the position at the top of the curve, of the distribution curve. And then we have the width, which you can see here is about like 100 millimeters, and this goes in both directions. So we can also see that this issue starts at about 350 millimeters and goes until 550 millimeters. And we also have the amplitude, which could be linked to the whole regression model as well, to indicate the overall condition of this fault or of the door in general. And taking this also into account, and if we plot this data on a scatter graph, for example, we have then the position on the y-axis here on the x-axis, the width on the g-axis, and it was interesting to see that we had really clear failure patterns with this kind of algorithm, with this kind of function, which we could also afterwards clearly identify with historical data. So we made cross references, we made double checks with historical CMMS data, and to match those failure modes with failures we had in the past, and this was a really successful task. We are really confident with the type of failures we can see with the data with this kind of model, which also occur or have occurred in the past on the fleets. But I have to say that we're talking about failures, but failures also talking about the PF interval. They are like abnormalities, so there's still there's like a potential for the fault. There's not yet a fault, and those can be also seen within there, and they have even the same pattern. So within here you can see different type of amplitudes, because the size of the circle represents the amplitude, and we have some smaller amplitudes, some bigger amplitudes, but they're all clustered together in this kind of region, this type of failure mode. And this is really interesting to see and really promising, also in terms of giving more precise feedback to the maintenance operators, where to look at when carry out the maintenance exam on the door. So they got the precise information. It's this type of failure. We could even include an example what to carry out. So what type of part they have to change afterwards. So yeah, this is kind of the summary of the development which we are doing so far. And this can be either done by correlation similarity or by unsupervised key mains clustering. There are different options how to analyze this. Yeah, and at the end, it's just maybe if I have maybe 1-2 minutes time, like challenges and outlook and opportunities for the work we do, the digital work we are doing is one thing I came across is the standardization of diagnostic and sensor data. Yeah, trains are no cars, so trains are highly customizable, and we're ending up with different OEMs with different type of doors, and hence the data is different from train to train. Even though you have maybe similar platforms, but they have maybe then still a kind of different OEMs in for their components. And this is one of the biggest issues when you ever set up a quite expensive digital solution and a prediction model. You want to make sure that you can use it for something else as well. And it's the easier whenever the raw data we are considering for this kind of model is standardized, the easier you can apply those models on different fleets and different trains. And this is something where we have to work on in the future, is to get an idea how this standardized model data model should look like. Another thing is to increase confidence in digital solutions whenever we are implementing those condition-based maintenance or predictive maintenance solution into a maintenance regime. We want to make sure that they are precise and they're doing their job properly, because if they're not, then we lose trust in our solutions and our products. And even though if they have fixed maintenance intervals, if they stick with and they're happy with this, and we come and introduce something new, we have to convince them with this kind of product. And yeah, the last two things is combine expertise and digital know-how. Previous sessions on RIA, I saw the introduction of a railway college in the Midlands with a specific digital module, which I really liked, but also the University of Birmingham is now introducing a digital module in their MSc program. So this is also something I think is really important for the future, to put this both expertise together. And last but not least is we have to drive innovations, digital innovation in rail in all sectors, because at a certain point, I'm sure that we can combine them all together and create even something greater out of it. So sorry for overrunning, but if you have further questions, if you want to get in touch, technically you can get in touch with me. In terms of business questions, commercial questions, please feel free to get in touch with my colleague Luca Fracasi. Thank you very much.
Thank you very much, Christoph. Interesting stuff, and interesting to see the rolling stock side of things as well. Just time for a few very, very quick questions. I don't see any questions popping up in the chat. If anybody does want to ask Christoph any questions, please place them in there, and he can answer them in text form as we get as we have the rest of our presentations this morning. Just a few from me, Christoph. Is this entirely an internal effort at Siemens, or do you work with SMEs that might have particular specialisms in the area?
At the moment, it's totally internally. It was kind of a POC phase at the beginning, due to the fact that we are maintaining some of the fleets also internally. It is also an interest from Siemens to provide such solutions. And to provide it internally, to use it also internally. So therefore, yeah, the moment is, but it doesn't mean that this cannot be go on in the future and as a collaboration, for example, with academia or with another supplier, for example.
Sure. So Giuseppe Varial has just asked in the chat, have you managed to make any changes to the maintenance regime using this approach?
To the regime at the moment, not now, because as I said before, we really want to make sure that this model is really precise, and we want to test this and want to evaluate this in a proper manner before we include this into a maintenance regime. What we usually do is we can set alerts, and we can create this work order so that we have maybe more corrective maintenance or even preventive maintenance tasks, which are additionally to the planned ones. With them, we can then decrease the technical incidents, the reliability, or increase the reliability at the end. But this is definitely the goal, and this is like we go step by step. First of all, we want to have this model running smoothly, and then this would be definitely the next step. Yeah.
Sure. It's good to see you. I noticed on slide 9 you were closing the loop because you performed the maintenance and you saw the curve return back to its natural state. I assume you're working very close. So something that resonated with me from the first presentation this morning was that the software it's being developed with the customer in mind, so that agile mindset and a new release every few weeks and getting that feedback. I assume you're doing the same thing with your internal customers in the depots. Yes,
exactly. Yeah. We have even tools that I can get this feedback by myself. So we are monitoring this. We have different type of CMMS dashboards, for example, where I can double check those results day by day and can see like how this true positive rate changes over time, for example. But yeah, we also have an internal work group where we discuss those results.
Wonderful. Okay, thank you very much, Christoph. Great to have you along in a very interesting presentation. Thank you. Next up, if you could stop sharing your screen for me, that'd be great. Thanks.
Sure. Yep. Thank you very much, everyone.
We have Dr. Nick Wright, who is a senior R&D engineer at MPEC Technology. Nick has worked on condition monitoring for 12 years, the first 4 of those in nuclear fusion and then 8 of those in the rail industry. He specialises in interpretation and analysis of railway signalling data in all its forms, and he currently is the lead of the data science research at MPEC Technology. And many moons ago, Nick and I used to share an office at Loughborough University, so it's great to have you on the call, Nick.
Thanks very much. Yep. So as Sam says, I've been working at MPEC for around 7 or 8 years now, and I've been working pretty much exclusively on remote condition monitoring, statistics, and machine learning. So I'm going to share my presentation. Can you see that? Okay.
Yeah, we can see that well.
Okay, great. So what I wanted to talk about today was track circuit data and level crossing data, and talk specifically around how you can interpret the data that we collect from these devices. So the best way for me to do that in the time available is probably to show you guys examples of good data, when the equipment's working properly, and show you examples of bad data when faults occur, and point out the sort of things we're interested in. Okay. Before we start, I'll give a quick introduction to MPEC. So we are a hardware and software products business. We have 22 employees split between software development and electronics production. We were founded in year 2000 and we were bought by the Traxys Group in 2011. We turn over approximately £5 million annually, with a group turnover of approximately 45 million. Key thing about MPEC is that we own all of our own IPR, so that's both for hardware and software. We have framework contracts to supply data logging hardware and RCM software to Network Rail, CSX in the United States, and Sydney Trains in Australia. We've got 20 key UK rail clients, 10 clients overseas, and we've deployed approximately 19,000 data logging devices. In terms of the data we collect, we've collected over 10 billion data events, and that's across roughly 70,000 assets. We provide data logging equipment for all sorts of railway signalling equipment, including track circuits and level crossings, which is what we're talking about today. And we also provide a software application called Centrix. Centrix is a cloud-based RCM platform that stores and analyzes data. You can use it to replay data on a graphical map, and it also provides alarms and alerts to engineers when anomalous data is spotted, which could indicate equipment degrading. I'm not going to talk too much about our data logging products because that's not the point of the session today, but just very quickly, this is our SA380TXL data logger. It's a low-cost data logging device. Typical applications for this include points and track circuit condition monitoring, and it can provide this data to both Centrix and the NR radar platform. It can be used anywhere in the world because it comes equipped with a GSM modem and also an Ethernet connection. This is our oldest product. This is the SA380. It's a high-capacity digital event monitoring device. One of these boxes can monitor 384 relays, and you can chain these together in a master-slave arrangement to monitor up to 3,072. This is our newest product. This is the SA380 IT busbar monitor. It continually measures earth leakage current on up to five different circuits. You can connect any combination of AC or DC circuits you like. It can detect transient earth faults, shorter than 7.5 seconds in duration. It monitors trends in insulation resistance to spot degradation, and additionally, you can use it to monitor supply voltages and earth leak resistance. Finally, BTI21 sensor. This is a multi-purpose AC sensor. Typical applications for this include track circuit monitoring. So we're talking about things like vane relays, retracts, TI21s, and you can connect 8 of these to a SA380 data logger via RS485 to transmit data back to Centrix. So I'm going to start by talking about track circuits. I'm going to show you 3 different examples of track circuit data here. So we'll start with DC tracks. So this is a screenshot from Centrix showing a single track circuit occupation. So the chart there at the top, that shows the current measured over the track relay. The bands on that chart there, the colored bands, they show what we have measured as like the typical clear current, the typical occupied current. In the table below, we can see all of the data points that we've measured at the end of this occupation. So we've got a measurement of the typical clear current for this track circuit, measurement for the typical occupied current. And we've also generated numerical scores which describe the quality of the application, quality of the occupation. So, for example, you can see here, the rising transition score. So talking about the rising edge of this occupation, we scored 100% there, so it's perfect. And the occupied current score is pretty good as well, that's 81%. So good data from a DC track circuit will look like this. The bit in the middle, whilst the track is occupied, is going to be flat, very close to 0. The leading and trailing edges here, they're going to be they look like first order decay curves. And also the clear current, that should be very stable as well. So this is good current, this is good quality DC track data. This is what the engineers want to be seeing. So to give you an example of bad track circuit data, I've got a couple of charts here that were recorded during a failure. So on the left-hand side, you can see that the rising edge of this chart, around 554 there, you can see that it's not a smooth first order curve. There are some peaks and bumps in it. So this is something we need to look for when we're looking for degraded DC tracks. The sort of things that can cause this, maybe a joint starting to fail, perhaps lipping, maybe even cable damage. On the right, to sort of the casual observer, you might think this is a perfect occupation, but it's not. If you look at the section in the middle here, you can see that it's not flat at all. It's kind of bumpy, and where I've hovered my cursor over the chart there, you can see we're reading 5.4 milliamps there. And you see this data when you come across things like railhead contamination. It can also be generated by rolling stock as well. And the way you discriminate between those two situations is by looking at adjacent tracks. If bad data is being generated by a rolling stock, you can follow it along by looking at different sections. The next thing I wanted to show you is EduTrack 400 data. So this has some similarities to DC track data. This data, we collect it over a serial link from the EduTrack 400 receiver device. There's a diagnostic port on it, and that's what we sniff. We sample it at 1 Hertz, so 1 sample per second. The main differences here is this data is a little less granular because the sample rate is slower. You'll see that the falling and rising edges here are much, this particular application, they're almost vertical. But you won't get that first order curve on EduTrack 400 data. Actually, the length and duration of these rising and falling edges will depend on what the size of the tune zone that the train's moving through. It'll also depend on the train's velocity. The thing that we get with EBI tracks that we don't get with DC track data is we get all the diagnostic information from the receiver device itself. So probably the two most, so all the data we collect, that's summarized in the table at the bottom there. Probably the most interesting part, well, we have an error state measurement here as well. So the device itself will report if it's got an internal fault, so we monitor that. And we also monitor the auto set current threshold, so the threshold at which the device says track section is occupied or not. So we can keep an eye to make sure that that's been calibrated properly. And we also generate numerical scores here for the quality of the track occupation. And with these numerical scores, both for DC tracks and EBI tracks, you can plot these on a chart and you can trend them over time. So you can look at the performance. You can look at the performance of the asset over time, and you can also use that score to triage and sort of find out which of your assets is performing best and which of your assets is performing worst. So I'm going to show you a couple of examples of data collected during faults. So this should be, it's very obvious that something's gone wrong here. So the chart on the left, that was recorded on the 14th of October 2020, and the chart on the right is on the 22nd of October. So they're about a week apart. You can see that the occupied current here is pretty unstable. We're getting lots of peaks and troughs in this occupied current data here on the left. And you can see a week later, it's actually got quite a lot worse. And the scores that we assign to each of these occupations reflect that as well. What's happened here, to me, this looks like railhead contamination. And it's sort of slowly getting worse over time. So we can pick that up. So this track circuit here has some very big problems. You can see the clear current here at the top is all over the place. And you can also see the occupation current here as well. It's not following that flat kind of bathtub shaped curve that we'd normally expect. Data like this would indicate perhaps the transmitter unit's got a problem. It could also be a problem with the tuning circuit. If we're not monitoring the transmitter device, the only real way to tell is by doing an inspection. But this is an example of, yeah, a very, very bad, unhealthy track circuit. The last one I wanted to show you was HVI track circuits. Data again is somewhat similar to EBI tracks. HVI track circuits work by passing a pulse train between a transmitter and a receiver. The data logger here is counting pulses and looking at the RMS current of these pulses, and it reports back at intervals. So we get the same sort of data rate, maybe a little bit higher, but a similar sort of data rate as we get on EBI tracks. We also measure the current not associated with the pulse. So we've laid that noise current here in my table at the bottom. And we also we've also built in a channel to our data logger called a pulse conflict channel. Adjacent HVI track circuits, the pulses are different polarity. So if our receiver unit is detecting pulses of the wrong polarity, then we can raise an alarm on that because that shows a joint's failed. I've got an example of that in the next slide. So this chart here, there's quite a lot of data here, but the interesting parts are the yellow line there that represents the impulse RMS current from the HVI track circuit. At the bottom in red and orange, that shows the state of the track relay, and our pulse conflict channel there is in the middle in blue. So from a signaler's perspective, it looks a bit like a track flick. You can see the state of the relay on the bottom there. There's sort of there's a little flick, and then the track drops for maybe 3 or 4 seconds or something like that. And then just after that, we can see the pulse conflict channel has gone high. So what that indicates to us is that a joint has failed. Now I can show you some data from level crossings as well. This is a screenshot again from Centrix. This shows our graphical replay facility. So all of the data that we collected from this site is displayed on the map. And you can, this is an animated map, so you can play through this data. You can also display the data in real time. We've got a list of all the digital events we've recorded there on the left, and you can scroll up and down, basically replay what's happened on this site. It's designed to mimic traditional signals panel. Typically for level crossings, we'll use an SA380 because the main thing we're interested in here is digital data. So you can see on the right there, and so on the bottom right as well, we've got timings between relay events, so we can see how long the barriers have taken to rise and fall. You can see the timing of the lamps. We've also got a wireless barrier angle sensor on this site too. So we've got the barrier angle there in the middle next to the wig bags there. And the sorts of things we're interested in are mostly around timings of events. We can set up alarms as follows. So the things I've listed here are things we should alarm on. So road lamp timing, barrier raise and fallen times, barrier hunting as well. You'll see that if your AMR relay is flicking on and off, that indicates that the barrier is hunting. Stuck tread alarms, and also time taken for a train to arrive at a crossing. So this broadly reflects the SMS. This table here summarizes that information with a little bit more detail. What we can do in addition to having, so if you look on the column on the right there, in addition to having sort of fixed limits that reflect what's in the SMS, we can also look at the trends as well. So we can look at the trends of how long the barrier is taken to rise, for example. And if it looks like the raise time is starting to degrade, we can spot that. We can alarm that. So this is another level crossing site. This is a site using a HXP3 predictor. I'm showing you this one because it is our customer has put a lot of data on this site, a lot of data on this map. So there's quite a lot going on, very high data density. And all of the things on the right there, these are all the things we can measure from a HXP3 predictor. So there's tons of digital data from that. This site, there was a wrong side failure on this site too, so that's why I wanted to use this as an example. I can show you what went wrong in this using these charts here. So these three charts, they've each got 3 bits of information on them. In black, we've got the HXP3 receive level. So this tells you how close the train is to the island. The shaded purple area shows when the island was down, and the blue shaded bit shows the phase angle measured by the receiver. So the top chart, this was recorded, quite a long time before the wrong side failure occurs, and you'd consider this normal. So if the train is traveling at a constant velocity, you'd expect this black line there on the left to be sort of mostly straight, and you'd expect the same as well from on the right-hand side when the train is leaving the crossing. The chart in the middle, this was recorded 1 day before the wrong side failure, and it looks okay, but if you look in the middle there, just after the island is finished at 12:28, you can see the black line here, it drops before rising. That's very unusual. We can alarm that. And this chart at the end, this shows the actual failure. So you can see at no point did the barriers fall here. The train has essentially disappeared. So this is very dangerous. The train goes across the crossing with the barriers open, and something we want to avoid. We can spot by analysing like the HXP3 receive level. We can spot this sort of thing in advance. If I've got time, I want to show a couple of videos just to give you a flavour of how Centrix can use. There's a lot of features in Centrix, but I'm just going to show you 2. So hopefully my video is playing now. So this shows how you set up a points alarm in Centrix. I'm just going to fast forward to save time here. Okay, so when you set up a points alarm in Centrix, you can pick an alarm sensitivity. So if you want a very sensitive alarm, you can have that. If you only want alarms when the performance of your points is very bad, you can pick low sensitivity. The alarm thresholds are generated by analysing historical data. So in the 2 date fields here on the right, we can pick sort of a range of training data for our alarm. You can create alarms with lots of assets at once. So here we'll just pick these 2. Whilst the alarm is being generated, you can see here that this little running indication on the left shows that Centrix is analysing the data and trying to come up with some alarm thresholds. Alarms can also be given a label like this. So this is like an email distribution list, so everyone on your team can get an email if something goes wrong with your points. And now the alarm thresholds have been calculated. It shows you what the current alarm thresholds are and what the new ones are. So that's how you set up a points alarm. It's easy to do it automatically. And now I want to show you what it looks like when a points alarm is raised. So each time a points alarm is raised, Centrix will generate a problem page like this. And the purpose of this page is to give the engineers all the information they need to know why the alarm was raised, and also some contextual information to help them decide whether they want to act on it or not. So for this alarm here, you can see that it's the process max threshold. So what that really means is we've raised the alarm because the points motor current here, if we exclude the inrush current and just look at the current that's recorded whilst the switch blades are moving, you can see that there's kind of a peak there. So on the chart on the left, the trace which caused an alarm raise is marked in blue, and you can see there that around 2,000 milliseconds in, the motor current has risen to about maybe 4.5 amps, and in red, the sort of the grey red, the sort of brown red trace there, that was recorded on the same machine a week ago. And so you can see there's a big difference there. Something like this might indicate sticky lock. Maybe the machine needs some lubrication. We can see on the right hand side as well this histogram, like the trend of, well, you can see the distribution of peak motor current over time. You can see there's a sort of bimodal thing here going on. So the performance of this switch has changed quite dramatically. There you go. So the alarm thresholds are marked here as red, and you can overlay traces, you know, from the previous day to previous week, and also moving the other direction. And below that, we have a scatter plot here. So on the x-axis here, okay, so on the y-axis, we've got our peak current, and on the x-axis, we've got swing time. And you can highlight most of the recent points movements, and you can click on these points to see the motor traces themselves if you want to. And the green shaded area shows the typical performance band for this machine. So you can see there's definitely two distinct performance bands there. So I will rapidly bring this to a close. At the bottom here as well, we can see the trend over time. So something switch has happened on the 5th of June. We've got a facility as well for engineers to make notes. So there's equivalent things for track circuits as well, equivalent things for level crossings and Centrix too. I just thought I'd show you that because that's a nice illustration. So that brings me to the end. I've got my email on the front slide here. So if anyone wants to talk to me about Centrix or interpreting data in general, you can get in touch with me at this address at the bottom.
Thank you, Nick. Thank you, Nick.
I did run over, didn't I? A little bit.
Only by a minute, so we've got time for one quick question, if I may. It seems like you can interpret lots from simple current logging with your track circuits. How automated is what you were talking about, for example, with the potential lipping of joints and things? Is this something you've automated into the system, or is it something that's currently R&D and you're looking at automating?
So it depends. It depends on the asset. So for points, we use a classifier which can pick out certain conditions like sticky locks. We do that for some types of track circuit asset as well, but not all of them at the moment. We sort of, as it's something we give to customers when they ask for it. Generally, yeah, we do when we're on.
Is that something that's a UK export at the moment? Are we exporting that to Sydney, CSX?
Yes, yeah, we have. Those are probably two of our biggest overseas clients. Yeah, we have clients in various countries. Yeah, so this is a proper UK export.
Excellent, great to hear. Please do stick around for the informal networking at the close of the call. If anybody's got any further questions for Nick, please do pop them in the chat, and Nick will be able to type a text answer to those. Thank you very much, Nick. Okay. Next up, we've got two shorter presentations, not quite elevator pitches, but 10 minutes in length. And first of all, I'd like to introduce Dr. Saeed Fararooy from RCM Squared Limited.
Hi. Hello, everybody. Can you hear me?
We can hear you well, but we can't see any slides yet.
No, sure. I'm sharing the screen. Let's see. Okay, so you can see this one now, hopefully.
Yes.
I've also got a short video presentation, but I'm going to start with the slides. And I'm going to pick and choose. But let's go from the start. Right. So my name is Saeed Fararooy. I have experience in RCM, and our company RCM Squared was established in 1998 as a lecturer in Birmingham University. I was doing a lot of the work that I can see continuing both in universities and by industry, including, for example, electric door condition monitoring and track circuit monitoring and point monitoring. This project is more about track and structural health monitoring using optical fiber sensing, for the main reason that our sensing will provide very accurate, precise measures of parameters we're monitoring, which is acceleration, vertical acceleration, and strain and temperature, and is immune to EMC. So the project was funded by Department for Transport, delivered by Innovate UK, and is focusing on void and crack growth monitoring at the crossing nodes. And we identified the interface with switches through a cloud solution. So because we found that in the flight control rooms at different network rail sites, you still have no fault found and no explanation, a very clear explanation of what can go wrong. And we felt that because the crossings is at the interface between different disciplines, train, rolling stock, the signaling, and the track is a permanent way, you need to really combine this, and we focus on structural health monitoring. So I'll explain about the motivation, the previous research, what we did, and what we achieved. Obviously, predictive maintenance is to help with improving worker safety, avoid red zone working, improving availability of services, with, and also asset life extension. The work that we've started, I mean, actually, in the first proposal I did to use fiber optic sensing for bridge bashing was in 1996. So the technology is not new, but this work you can see is using similar sensors that we use, but for train type identification and axle counting. Of course, with axle counter, if you want to implement it, it will be SIL4. In our case, we are doing predictive maintenance, and we are following SIL2, safety integrity level 2 requirements. So you can see that the signature you're collecting is quite rich, and you can get a lot of things provided you can separate them from each other. And in order to explain what the background was, that this project, we started a collaborative research back in 2018 and 19. We did laboratory testing, we did modeling, finite element modeling. We had samples of the track with different crack slots, and we looked at the measurement noise and the statistical analysis of that. We had an installation at Dockland Light Rail. This is in 2019 as well. And we found that this was interesting because before and after tamping, we were lucky to collect data. And as you can see, the green is actually when the track had void, significant void. The deviation actually, which is not shown very clearly here, is about 12 up to 12 millimeter deflection. And you can see that the sharp kickback that you get with two wheels of a bogie going over our sensing is damped. Also, the strain levels that the track is subject to is double. So there's a lot of features that we realize that we can exploit for our research. So this we did a number of innovations, because the experimental work that we did in Dockland Light Rail was basically just a laptop with some interrogator, some sensing, and we realized that we cannot just that would not suffice, and we had to develop a cloud solution. We had to develop certain digital twin, digital model, and develop various elements. And so our project, and I want to present as a whole, because although the subject today is about data analysis, I wanted to show you the challenges we had to go through to collect the data and make sense of data. So this is a typical crossing with different elements. Since you're going to get the slides, I'm going to go again fast on this one. These are the two sites, one of the two sites that we wanted to install our equipment. This was in our proposal in March. In fact, I visited this site 3 years ago, Shalford Junction, which is between Guildford and on the route to Portsmouth and Reigate. But we also researched recently on recent paper about railway void research, and that's where you have the infrastructure track stiffness mainly reduced as a result of problems with either the geotechnical issues, drainage problems, or sometimes broken sleepers, especially at the crossing because they are wooden, or hanging sleepers, etc. So the main thing is to be able to measure excessive track deflection or longer than or larger than 7 millimeters. There are different methods used, very simple displacement measurement and high-speed photography, but we believe that those were not robust, and that's why we focused on using fiber optic sensing. So typically, this is how a void is monitored and measured, and you can see that when we don't have this damping as a result of the for example, sufficient ballast and sleepers and etc. supporting the infrastructure, you get a lot more deflection and a lot more strain applied, and that's where just to expand on what we did before, you have the wheels and the strain pattern when there's no void. It's just straight after tamping, shows clear kickback between the two peaks that you get from the two train wheels, whereas that's significantly different and higher strains when you have the when you have void. So our approach was to use multiple sensor fusion. So we use accelerometers as well as strain to get high signal to noise ratio, normalize against variations in weather, temperature, especially even direct sun, and then use a combination of model-based and data-driven technology. For model-based, we use this digital twin. And of course, I'll explain that we installed our equipment in April, and we are collecting and doing statistical analysis on this. But to show you the components that we had to build, first of all, we built a cabinet, and in certain areas we couldn't get mains power, so we developed a prototype solar panel and wind power, and we developed and built and prototype development and building of a clamp, simple clamp to hold our sensors. We used sort of systems engineering and Capella system architecture. We had to go through defining our product and going through assurance. For example, we organized a hazard identification session back in November, and then prepared all the documentation and achieved the safety review panel approval by OptRail RIDC to implement our system. That was done in March, April this year. Carried out failure mode analysis and fault model, because basically we use this as a process for what's called design for reliability, DFR process that OptRail follows. And we had to develop new IP and develop the prototype. We developed a cloud solution, which I'll touch on that, but briefly, and then I'll show you some of the results.
Just to say, you have 30 seconds left, Saeed.
Already out of 10.
Yeah.
Oh, okay. So okay, right. 30 seconds.
1 minute, absolute max. Yes, it's 10 minutes.
I see. So I only understood from your introduction that we were one of the speakers that we have half the time with other people. And okay, anyway, so I need to go fast on that. This explains our modeling and checking against the references. We modeled a partially hanged sleepers and collected data. This shows the difference between the partially hanged sleepers, much bigger vertical displacement and strain. So this is the digital twin part. This is how we install the equipment. This is the current signature data we are collecting. We are from strain sensors and temperature sensors and fast Fourier transform analysis. Probably this is one of the critical bits that I can focus in the next 10 seconds, which is the fact that we have a strain array at the crossing nodes, and we now can very accurately measure the stresses at the transition area of the switches and crossing. So this is quite novel. I haven't seen any similar work done in literature, and we're very interested to work and collaborate with other companies to develop this further. This is giving a lot of information and about both train defects as well as the stress faced by the track. That's it really. So yeah. So because I want to leave some time for people to ask any questions.
So we've gone over the question time, I'm afraid, but if you stick around for 10 more minutes, there will be an informal networking session at the end of the call. And if anybody would like to ask Saeed a question, then please do pop it in the chat, and the full slide deck will be shared after the event. So if you would like to read more into that, then yeah, the slides will be shared by RIA after the event. Thank you very much, Saeed. I'm sorry that was a whistle-stop tour of your technology, but without further ado, I'd like to introduce Chris Jones from Frazer Nash Consultancy, and I believe Barry Lowe from Hull. Is that right? Yep. Hello, Barry. And they're going to be talking about the repair program. I'd just like to note this isn't directly about maintenance, but we've included this in the schedule because it's an example of what can be done for the railway with our existing data streams and using data and interpreting existing data streams, sorry. So it fits the theme of the session in general. So over to you, Chris and Barry, 10 minutes as well.
Yeah, don't worry. We've had a practice, Sam. We'll be 10 minutes, almost bang on, all being well. Right. So thanks everyone. So I'm Chris from Frazer Nash. Those of you who don't know Frazer Nash, we're engineering consultancy of about 900 in the UK and Australia. And between Barry and I today, we're going to give a brief overview of repair. So I'll just share my screen. And all being well, everybody can see that. Right. So what is repair? Well, first thing to say about repair is we're very grateful to the Railway Industry Association for the Unlocking Innovation Award that we picked up in November. So a very relevant topic for this discussion. We're going to give you a whistle-stop tour of exactly what repair has been all about over the last 18 months. As Sam mentioned in the intro there, fundamentally, repair is about making use of existing data. And what Barry and I are going to explain is how we've taken a data set from the Logistics Institute at the University of Hull and made use of it using some defence sector technology to predict delay propagation across the rail network. So what does it do? Well, it's a tool. Repair stands for Rapid Evaluation and Planning Analysis Infrastructure for Railways. A bit catchy, but fundamentally it's about doing more with stuff we've already got. So Barry's going to talk about NR+, the data set behind all this in a second. But what repair is doing is bringing together machine learning technology and applying it to existing data to predict the propagation of delays across the UK rail network. And the back end of this presentation has got 3 short videos that will show you repair in use. What it's trying to do is provide insight from existing data and understanding what our assets are doing on the network so we can do a bit more with what we've already got. So conscious of time, I'll hand over to Barry to talk a little bit about NR+ and the kind of the backbone of data that sits behind repair. Barry, you're on mute, I think, Barry. We can't hear you.
There we go.
That's better.
Thanks, Chris. So the reason we need to just quickly talk about NR+ is, as Chris says, this is the data that's being used to feed the repair solution. It's also the platform on which we deploy the front end for repair. So we need to understand a little bit about what it is. So Chris, just next slide there. We developed as the University of Hull Logistics Institute the NR+ platform. We started in 2018, 2019. We got some funding from TFD through Innovate UK, and we developed this platform which essentially tried to consolidate and integrate all the data that's used by planners to plan the routes for freight trains. Historically, these documents are all in separate little files and sources. Some of it digitized, some of it's not digitized, some of it's semi-digitized, and we just tried to bring this all together. The problem that we're solving is that planners are taking a lot of time and needed a lot of experience to use all these different sources, interpret them, relate them to each other, etc., just in order to find which trains is cleared for which routes on the network. So on the right, you can see the architecture there. We've got all these different sources which we digitized into two databases, one being relating to the infrastructure, the layout of the network, and then on top of that, what is the gauge clearances, the weights, the length, the maximum capabilities of the network on any spot. And then we also have a database of schedules. So we've got 10 years of all the historic schedules on the network, as well as all the movements of trains updated up to the minute for the last 4 years or so, which we can then use to interpret and analyze the performance of the trains on the networks and the capabilities of the network. So having got this database, we're exposing it through a set of APIs, so we can use it for external parties to be used. We also built our own set of applications on top of that, which is deployed through a web interface. So if you can just go to the next slide there, Chris. So the type of data that we've got in our database, there's more than 600 pages of sectional appendices which defines the gauging clearances and the axle weight limitations on the network. There's 10,000 tables in Excel format of load books which defines the trailing weights and lengths that's allowed for trains. Then we've got more than 10,000 tip locks that we had to position exactly on the network to make sense in terms of the rest of the data, etc. And then we also got the 10 years now and 4 years of actual movements and 10 years of scheduled data, which we've got full details of in our database. Having all of that, we also have a team in place to keep it all up to date. And we can now use applications. The example here is just a map where we show all the loading gauges, what's the maximum loading gauge anywhere on the network. On the same map, we can also do the maximum lengths, the maximum weights, what kind of electrification is available, where on the network, etc. And we can also build maps, so you can ask a question. You can say, where on the network can I run trains more than 450 meters long with high cube containers on that weighs more than 2,000 tons? for instance, and it will show you where that is cleared. Next slide, Chris. We can also then do find, for instance, what is the shortest or the best route between 2 points for a specific configuration of train that is cleared for. And also the historic data comes in here, where we can then evaluate and say, we can also show historically what routes have been used to connect these 2 points. So this makes the planner's life much more easier, and also exposes the data to people who are not expert and experienced planners but may want to analyze this type of information. So it makes it much more usable and accessible. And this is the data that we could then provide to Chris and his team.
Perfect, thanks, Barry. So what we just heard there is the kind of run through the data set, and what Repair has done, and it kind of at its heart, is take that massive amount of timetable and schedule data and apply machine learning to it to build a behavioural model of the UK rail network, so that we've got the ability to understand, in the instance of a delay, when we see a new delay come onto the network, how does the network respond to that and how does it behave, so that we can use that behaviour model to predict the future. So we're doing some analysis on old data using machine learning to build a behavioral model that allows us to do some analytics and predict the future. As we developed this work, it was for RSSB and Network Rail, I should have added at the beginning. We had quite a few partner organisations involved who helped steer the work. So just a list on the screen at the moment about the people that were involved in helping steer the work, but really help give it that kind of industry end user focus. So what I'm going to do now, just to finish up, the last kind of 3 minutes here, is just show you what Repair looks like, and give you kind of 3 instances. There's lots of different ways and means we can use it. So what you see on the screen at the moment, hopefully the video is playing across my internet connection all right, is a view of the UK rail network. So we're pulling on the geospatial data from NR+, and you can see in the map there all the train lines around the UK coloured from white, where there's currently no delay on the network, through yellow, orange, and into red, where we've got delays in excess of half an hour. What we can do here is a bit like using Google Maps. You can zoom in, you can look at any particular part of the network, and you can interrogate what's going on in the network by clicking on the lines. And what we see pop up on the right-hand side here is an example for that particular tip lock to tip lock location, to geospatial location. How does the delay look for the last 3 hours, and what does it look like for the next hour? And it's these red numbers at the bottom you can see being clicked on now, which is the predictive engine kicking in, where we're able to take real-time delays from the trust database from Network Rail and use the behavioural model we've developed that sits at the heart of Repair to predict what's going to happen in the future. And in this instance, we can see on the right-hand side, we're expecting delays here to increase, but then slowly taper off. So anyone interfacing with the Repair in this way gets a real-time live view of what's going to happen now, what's been happening for the last 3 hours, and predicting hours into the future how the network is going to respond. So a useful tool. Next video I want to show you is pulling on some of that route finding capability Barry mentioned. So in addition to being able to just show us what's happening with the network and how the future is going to look, we're able to ask it for what's going to happen between 2 destinations. So in this instance, I'm going from Southampton to Leeds. I'm asking it to go away and search based on the consist of train that I currently have. This is a freight focused project at the moment, but it's equally applicable to the passenger domain. Show me viable routes through the network in accordance with the schedule. And what we can see on the right-hand side here is the kind of grey bars indicate the schedule time for 4 services leaving in the next 6 hours. And the red bits are the likely delays that we're going to suffer as we go down those routes. And that's using that predictive behavioural model to understand exactly what delay is going to look like. Really useful for planners to be able to understand exactly what's going to happen before they set off, and that's kind of where the Repair main use case is aimed here. And we can flick between different routes and see where delays are going to crop up and where delays are likely to clear. One final viewpoint here came out of user feedback was crew availability. So actually being able to have a cumulative travel time displayed. So here we're seeing hour by hour where the train will be along the track, so that we're able to say, to visualize very readily that if we've got a 4-hour delay creeping in, whatever it might look like, we know exactly where we're going to be and how much crew hours we have left, so we can make appropriate decisions on crewing and staffing before we're setting off on our journey. And that's the crucial thing here. It's the predictive element allowing us to plan better. And then just one last final slide here, a Network Rail use case dropped out here around possession management and bits and pieces around that. So I mentioned before, we're pulling real-time delays from Network Rail trust system into the predictive engine to predict what's going to happen based on what's happening on the network right now. What we've done here is sever that link to real-time data and allow the user to insert their own delay data. So in the example here, I've just inserted 28-minute delay in Warrington, and it's now seeding the behavioural model with that delay and allowing us to predict what's going to happen to the network in the instance of that. So if we want to have a possession of a line where it's going to be blocked for 6 hours, let's put a delay of 6 hours or an infinite delay in that particular line, and we can look at the delay impacts on the surrounding parts of the network. So where do we need to do capacity studies and target different bits and pieces? And we can see in this simplistic example, we've put our 28-minute delay in at this particular instance. The behavioural model is telling us that in the short term, in the 15-minute window, we expect that to drop, but actually the long-term behaviour of that particular part of the track is likely to see significant delay increase. And that's what repair is about. It's about helping people to understand what's going on the network using data we've already got. There's no novel new data been integrated as part of this project. It's using things we've already got and applying technology, in this instance, from the defence domain. And hopefully we're somewhere near 10 minutes there, Sam, all being well. Contact details on the screen there, keep people involved. Nicely, I think we're leading straight into general questions now, so I'm quite happy to take any questions. Oh, I think you're on mute, Sam. Yeah. Oh, Sam, you're on mute, Sam. We can't hear you.
I nearly made it all the way through the call without mucking it up. Thank you very much. Interesting stuff. We are leading into the informal networking session, but a couple of questions have just popped up in the chat. So first of all, Martin Mason, who presented first this morning, has just said that it's wonderful intelligence. So some good feedback for you there. Ant Monaghan says, is this data set and service available? So I assume, Ant, either if you want to pop your camera on and discuss that question, I assume you mean to third parties who aren't Network Rail, or?
Yeah, so I'll give you. So at the moment, this was a grant agreement as part of the Data Sandbox Plus competition, and we've taken it to Technology Readiness Level 6 in its current manifestation. Stage it's at the moment is it's out for trials with the FOC community, so the freight operators are having a play and invite Network Rail into that space as well. So that's the kind of repair aspect. The data set at its heart is probably one for Barry. So I mean, if people want to get involved in the trial of repair, I'm all ears. I don't think there's any issues at all there. People want to get involved and help us kind of steer that development. But Barry, do you want to say something about NR Plus?
Well, I think quite similar. On the one hand, I want to say watch this space. We're in the process of formalizing exactly how this is going to go to market or be exposed to people. In the meantime, feel free to contact us. We certainly welcome collaborating or working with anybody in the meantime in ways that make sense. So feel free to contact us in the meantime.
Wonderful. Ian Maxwell just says, repair looks great. Do you have any evidence that your predictions are correct?
Yes, that was a key focus of every stakeholder involved. I think the believability factor is actually absolutely crucial, isn't it? The answer is yes. So the way we actually implemented the development was we started off by training the behavioural model with 1 year's worth of delay and achieve timetable data, and extracted a number of different bits of the data set out of that at random. Across, I think, 6 locations to start with, and obviously the classical machine learning approach. We then took those extracted data points and used it to validate our predictions. We also then took some data from further back in time when we extended the kind of period of which we were training the model over, and again used the data unseen by the learning algorithms to validate the model. At the request of RSSB and Network Rail, we also looked for some particular types of event on the network. So it might have been something around leaf fall season where we know there were a lot of delays going on in one particular point of the network that someone wanted looking at, and we used those as use cases to do some targeted validation. So the kind of validating the predictive engine, we did in that way, which is fairly classical for machine learning data science. There's another half of the validation, which is the user trials, because proof is in the pudding, really, isn't it? And the kind of the engagement we're on, and we're about 3 months now into that, the freight operating company's trial process, is to ask them to tell us if it works and how well it responds in actual use alongside the day job to help decisions. And that's a crucial secondary part of that validation, Ian.
Wonderful.